We will begin with a quick review of the concepts that we have covered so far, which will be primarily what are some of the basic discrete time signals, and then what are some of the basic operations that we can do on the discrete time signals. These were some of the concepts that we have covered recently. I'd like to begin by covering that, and again looking at the topics that we want to cover in the first 2 weeks. The ones we have shown in green with a tick mark are those that we have completed: review of signals and systems, basic operations of signals, and discrete time signals, and particularly complex exponentials and sinusoids. So basically this is what we have covered. We will be covering the remaining topics in the next few sessions. So a quick review of the topics that we have covered so far. 4 basic signals that we looked at in the last session, where the first one was a unit sample delta of n, which has got only one non-zero value, which is equal to 1 at n equal to 0 and 0 everywhere else. So whatever is the argument of the delta function of the unit sample, that at that particular value of n, you will get a value equal to 1. Unit step u of n starts at n equal to 0 and then goes all the way to infinity with the value equal to 1 at all samples. So that is the unit step. An exponential is of the form a times alpha raised to the power of n, and this is particular case that we are looking at is a decaying exponential, which comes for the case when alpha is greater than 0 but less than 1. And then we have sinusoids, which are of the form a times cosine omega naught n plus phi, where a, omega naught and phi are real numbers, and we called omega naught as the discrete time frequency with the units equal to radians. So basically that is the representation of a sinusoid. Now looking at exponentials particularly, we saw that there were 4 categories of exponentials depending on whether alpha is greater than 1 or less than 1. You can get, if alpha is greater than 1, you can get a growing exponential, or you can get a decaying exponential if alpha is less than 1. So this is a scenario where you have alpha greater than 0, greater than 1. Alpha greater than 1. And then a decaying exponential is when it is positive but less than 1. Oscillating exponentials come when alpha is negative. So if you have a value of alpha that is negative, then you will see that there will be an oscillation. So basically, depending upon what the value of alpha is, if alpha is between between 0 and -1, you will get a oscillating exponential that is decaying. And then if you have an alpha which is between -1 and minus infinity, then you will see that there will be an oscillating exponential which will keep growing in terms of. So basically, this just to understand what is the behavior of the exponential functions. And of course, we are interested in the decaying exponential. We will see that there are many scenarios where we will be interested in the decaying exponential. Then moving on to the sinusoids, we said that the sinusoid is of the form a cosine omega naught n plus phi, or a sine omega naught n plus phi. The complex version of it will be e power j omega naught n plus phi, which can be split into a cosine term and a sine term. Again, the important thing to take away from this notation is the omega naught is called the discrete time frequency, and it is a quantity which has got units equal to radians. Compared to the continuous time frequency, uppercase omega naught, that has got a frequency which is radians per second. So the relationship between the discrete time frequency and the continuous time frequency is given for us now. Again, this will become more important when we study sampling, but at least for the reference, omega naught times Ts, that is the continuous time frequency omega naught times Ts, gives us the discrete time frequency omega naught. Units of omega naught, radians, units of phi is radians. So basically you have a cosine and an argument which is in terms of radians, for which you can compute the cosine value. So basically this is how a cosine function is defined. Now if the cosine is multiplied with an exponential, so basically you take the cosine term multiplied by a alpha power n, then you will basically get the superimposed behavior of a decaying exponential or a growing exponential. And that is what is shown if shown in this graph. Okay, so let us move on to the basic operations that we reviewed in the last lecture. We said that we can do basic operations. One of the most important and basic operations is the shifting operation, a time shifting operation. It is denoted as y of n equal to x of n minus n naught. So we looked at an example. If you had a sequence 5, 4, 3, 2, 1 starting at n equal to 0, that is x of n, the green sequence. If you want to shift it by 1 unit of time, y1 of n is equal to x of n minus 1. We showed in the last lecture that this corresponds to a delay of 1 unit of time. That means advancing the origin to the left, so it becomes 0, 5, 4, 3, 2, 1, where 0 now becomes the index n equal to 0. By the same token, if you wrote down y2 of n equal to x of n plus 2, that is like advancing the sequence by 2 units of time. So the index n equal to 0 moves from the value 5 to the value 3. So basically you have moved. So we call it a delay operation. It can also be an advance operation. So y of n is equal to x of n minus n naught. If n naught is greater than 0, we get a delay. Okay, so n naught is a value that is greater than 0. The sequence will get shifted. Now, by the same token, if n naught is less than 0, a negative value, then what will happen? You will see that it advances to the front. Now, useful for us to, one of the easiest signals in which we can remember this is saying, okay, delta of n, it is has a value 1 at n equal to 0. Delta of n minus 1 shifts to the right by 1 unit of time. So basically with the index equal to 1, it will have the amplitude equal to 1. Delta of n plus 2 shifts to the left or advances by 2 units of time, and at n equal to 2 minus 2, it has a amplitude equal to 1. All of these have got amplitude equal to 1. Okay, I hope you are comfortable with the discrete time signals, the basic operation of. After this, we looked at the property or the operation which is time reversal. So we said that it is like keeping a mirror and then doing a mirror image on either side. So for example, if I wanted to do x of minus n, then 3 is my midpoint, 3 is the point at which is index 0, 3 remains at the index point, and everything to the right moves over to the left hand side. So 2 and 1 are to the right, it moves over to this side, and anything from this side, from the left, moves over to the right. So x of minus n is sketched here. You can see that this is basically a time reversal. A sequence which is going in the positive direction now goes in the other direction. Now, if you had 2 sequences, you can do addition of sequences, you can do multiplication of sequences. You have to keep in mind that for every time index, you must take the corresponding value from sequence 1 and corresponding value from sequence 2. So for example, if I want the addition of 2 sequences, y1 of 1 will be x1 of 1 plus x2 of 1. Product would be x1 of 1 times x2 of 1. So you can do sequence addition or you can do sequence multiplication. You can also do scalar addition and scalar multiplication. Scalar addition means that you are going to add the same scalar alpha to all of the samples. So it will be alpha plus x2. And or if you're going to multiply by a scalar value, then what you will find is that you will have a scalar value that is going to multiply all your samples. Maybe a good point for us to look at a simple example and appreciate what this particular property is doing for us. So consider the unit sample sequence u of n. Okay, sketch the unit sample sequence. It has height equal to 1 at time n equal to 0, and at all positive values it is so n equal to 0, 1, 2, 3 and so on, and it has got a value equal to 0 at these points. Okay. Now look at a sequence which is defined by y of n is equal to u of n minus half, a scalar addition, but this is because the scalar happens to be negative, you can call it as scalar subtraction. Now very interesting to see what y of n will be. Sketch y of n. So wherever it is 1, it will take the value 1/2. So it will reduce in height. Okay, it will take on the value 1/2. So, all of these have got the value 1/2. Wherever it was previously 0, now it will take on the value minus 1/2. Okay, you see that there is a very interesting. Now, this is a way by which you have removed the DC component in the signal. Basically, the DC component was half, you removed the DC component. So, the addition of a or subtraction of a scalar means that the same constant is used for all the samples. And this is an example where we did a scalar subtraction. Now, by the same token, you can indicate the, by the way, this particular operation can be indicated as x of or u of n okay, added with a scalar alpha equal to 1/2 minus 1/2. This is y of n. So, basically sequence addition will be of this type. You can also think of addition of two sequences. Addition of two sequences, you can write x1 of n as one sequence, addition x2 of n, and this could be the output y of n. By the same token, you can multiply two sequences, you can multiply with a scalar. Let me also give you an example of a operation. So, this is an example where we do multiplication by a scalar. So, y of n is equal to alpha times u of n, where alpha equal to 3. Okay. So, basically look at the original sequence. Original sequence had all samples equal to 1, but now all the samples will be at a height of 3. Okay. All samples will be at a height of 3. This is original, this is the actual sequence y of n. It has got 3 as the height, all samples, and wherever it was 0, it continues to remain to be 0. 3 times 0 is 0. So, it looks like a unit step, but it is not at a height of 1. But so, scalar multiplication. Scalar multiplication means you take the signal u of n, you multiply every sample by a factor alpha, and the output y of n equal to alpha times, so in the more general case, it will be x of n, alpha times x of n. Okay. And this is nothing but if alpha is greater than 1, you get an amplification. You multiply it, the signal becomes larger, an amplification. Okay. And alpha less than 1, we get an attenuation. And very often in electronics, we want to either amplify the signal or attenuate the signal. So, depending upon what the application may be, and this is a case that where you can see how you can, by using a scalar and operating on the entire sequence, you can amplify the signal or you can attenuate the signal. And similarly, you can do addition of a scalar or subtraction of or addition of two sequences or addition of a scalar. All right. So, now we move on to the example that we were asked to do. I hope you had a chance to look at the example. So, we are given two sequences, the origin for each of them is specified. The first calculation we were asked to do was y of n, y1 of n is equal to x1 of n plus x2 of n. Okay, here are the sequence of numbers, basically adding them sample by sample. So, if you take the sample 0, it is 2 plus 3, which is 5. Sample 1, 3.4 plus 2, 5.4. So, basically you can verify. Similarly, multiplication, you multiply each sample by the corresponding value, take n equal to 0, you have 2 and 3, 3 times 2 is 6, and you can verify that all of the samples are multiplied. The multiplication by a scalar, you take the sample, 3 by 2 times, what did we have, x2 of n, not 3 by 2 of n, 3 by 2 times x2 of n. Okay. So, whatever is the sample value, multiply by 3 by 2. So, take the n equal to 0, 3 by 2 times 3. So, 3 times 3 is 9, divided by 2 is 4.5, and you can check all these samples. Similarly, you can also look at the fourth operation where you are asked to add alpha plus the sequence alpha equal to 2, you can verify. In all cases the origin is clearly identified. So, please go through and make sure that you are able to get this expression. All right. Then we went on to looking at the definitions. When is a signal finite length, or you call it as an infinite length sequence? Is it a causal sequence? If it starts at a point and then goes towards infinity, it's a right-sided sequence. If it starts at n equal to 0 and goes to the right, you call it a causal sequence. Similarly, what is a left-sided sequence, anti-causal sequence? What is a sequence that goes both, has positive and negative indexes of n? That's a non-causal sequence. And if it is a finite length sequence, we said that the expression for the length is n2 to, supposing it is non-zero in the range n2 to n1, both ends inclusive, then it is the other way, from n1 to n2. N1 to N2. So, the lower limit is N1, upper limit is N2. It is then you get N2 minus N1 plus 1, that is the range of, or the length of the sequence, and this is the range. Now, maybe a good way to refresh ourselves is to ask what U of n is from the basic definitions. U of n starts at n equal to 0 and goes to the right all the way to infinity. So, it is an infinite length sequence. Does it satisfy the condition for causality? Yes, there is no non-zero value for n less than 0. So, it is causal. Of course, it is a right-sided sequence. Now, U of n plus 1 is a sequence that starts at n equal to minus 1. So, U of n plus 1, if you sketch that, it is U of n advanced by 1 unit of time. Okay, so, it will have a value 1 at 0, it will also have a value at n equal to minus 1, and then all positive values it will have. Okay, so, this is minus 1, 0, 1, 2, dot, 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 dot. So, this is n, and then you have zeros in this region. Okay, U of n plus 1 is infinite length, it is right-sided, but it does not satisfy the condition for causality, because n equal to minus 1 has got a non-zero value. So, it is not a causal sequence, and it is not anti-causal either. So, basically we call it as a non-causal sequence. It is infinite length, non-causal, right-sided. U of minus n, you have done a mirror image of that. We looked at it in the last session. It will be infinite length, it will be left-sided. However, it does not satisfy the condition for anti-causal. Anti-causal means it must start at minus 1 and go towards the negative. It cannot have a non-zero value at n equal to 0. U of minus n has got a non-zero value for n equal to 0. So, we call it as non-causal and left-sided. However, U of minus n minus 1, which is a shifted version of the unit step sequence and the mirror image, that will be infinite length, anti-causal, left-sided. Now, U of n, if I told you that my sequence is expressed as U of n minus U of n minus 3, how will you sketch it for me? Sketch U of n starting at n equal to 0, you will get all one valued samples. N minus 3, starting at n equal to 3, you will have another unit step function. So, when you subtract these two, the only non-zero samples that will be left will be n equal to 0, n equal to 1 and n equal to 2. Okay, I hope you are able to see that. So, this will be, though U of n is an infinite length sequence, U of n minus 3 is an infinite length sequence. However, what we got through the operation was a sequence of finite length. Is it causal? Yes, because it starts at n equal to 0 and has only non-zero values for positive values of n. It is causal. Because it is finite length, you can define a sequence. It starts at n1 equal to 0, goes up to n2 equal to 2. You can take the expression for length and you can see that length n equal to 3. Okay. Now, by the same token, I would also like you to think about what is the sequence that will be given by U of n plus 1 minus U of n minus 3. Okay. So, this would be the answer for this would be a sequence which will look like this. So you will have a sample at -1, which is present and has the height equal to 1, 0, 1 and 2. After that, all the samples will be 0 valued samples. Okay, so this is what we will get, and this has a sequence n equal to 4. So you should be able to write down or sketch the sequences once expressions are given, and always go from first principles and sketch it, and then do the shifting if shifting is involved, and then come up with the final answer and give the observations. So these are some of the aspects that we have covered. So important thing to remember: causal, anti-causal. What are the strict definitions? Right-sided, left-sided. Non-causal if it has both sides, and any computation of length if it is a finite length sequence. Now, moving on, the last topic that we had reviewed in the last session was the aspect of sinusoids. We highlighted two properties of sinusoids. The first property was that all sinusoids in the discrete time show a periodicity in frequency, and the period is equal to 2 pi. So it's a very unique property, because such a property does not exist in the continuous time. In the continuous time, frequencies go from 0 to infinity. Here you see that there is a periodicity, and the periodicity we saw that start from omega equal to 0, you increase it, you start to see higher and higher frequencies. And then if you go beyond pi, it starts to decrease and then comes down. So that's what we show here. The rate of oscillations, it increases from 0 to pi and then goes down from pi to 2 pi, again increases, goes down. So all sequences, discrete time sinusoids, are periodic in frequency. Then we looked at the condition about the periodicity in time. If a discrete time sinusoid should be periodic in time, it should satisfy a very specific condition. Now, here again it is different from a continuous time, because in continuous time all sinusoids are periodic. You can take 2 pi divided by omega naught, that is the period of the sinusoid. On the other hand, in a discrete time sinusoid, we showed in the last class, 2 pi by omega naught must be equal to a rational number n by m. And we showed that if you can choose any value of m and you obtain an integer value of n, then that can be declared to be the period of the sinusoid. So if you look at an example, if I want sinusoids with period equal to n, we said that it must satisfy this condition: 2 pi by omega naught must be equal to n. So cross multiply, you will get omega naught equal to 2 pi by n times k. Now, whatever value of k is an integer, so or in this case, sorry, it should be equal to m, okay, times m. Okay, now m is an integer. M is an integer, and we are interested in positive values, because negative frequency is not something that we are thinking about now. So you can start with m equal to 0, 1, all the way to n minus 1, and then when you come to n, you will find that it's equal to 2 pi. So therefore, basically it will wrap around. So the number of distinct sinusoids which have got period equal to n is equal to exactly n frequencies. So, and those frequencies are 2 pi by n, 4 pi by n, 6 pi by n, and so on, all the way up to n minus 1 times 2 pi divided by n. So basically these are and this will be a useful result when we talk about the Fourier series representation. And but more importantly, at this point we are looking at the properties of sinusoids and their periods, and this is a good point at which we can summarize the results.